Hello, this is Ben Elliott's ENME351 Lab 4. So you can see my Arduino code. I start with initializing some variables and the serial monitor. Then in my loop, I have a timing loop there and there. I read the frequency from the potentiometer. I make sure that it's not equal to 0 because that would cause problems defining my time step, which I did in terms of dividing by 1 million by the frequency because I am using microseconds instead of milliseconds. And then I print the signal from the end scope to the serial monitor. So now looking at the graph and frequency and time domain graphs from the processing code. So for the 500 Hertz sampling frequency, only the 300 Hertz signal aliased, and it aliased down to around 200 Hertz. The other had expected frequency domain plots. At a sampling frequency of 200 Hertz, the 300 Hertz aliased down to about 97 Hertz, and the 215 Hertz signal aliased down to about 15 Hertz. Whereas the 175 Hertz signals displayed as expected. For a sampling frequency of 142 Hertz, all 4 signals aliased. So you can see the 75 Hertz signal aliased down to 67 Hertz, and similar aliasing occurred in the other 3 signals. Again, for a sampling frequency of 100 Hertz, all 4 of the input frequencies experienced aliasing. So here you can see the chart or table of the sampling frequencies, the signal frequencies, and the theoretical aliasing and the measured or experimental aliasing. You can see in nearly all the cases they're very close, if not exactly right. With one of the largest, or the largest error being 3 Hertz error, which is rather close to the experimental value. So you can see an example of my work for finding the theoretical aliasing frequency. So for a sample frequency of 142, 75 equals B times the Nyquist frequency of 71, which is 142 over 2. So then B would equal to 1.056, which would, using the folding diagram here from your slides, would lead to 0.9436. 0.9436 times the Nyquist frequency of 71 Hertz leads to a theoretical aliasing of 67 Hertz. And going up to the table, seeing 142 Hertz sampling, measuring a 75 Hertz signal, both the theoretical and experimental aliasing was 67 Hertz, as expected. So here's my paragraph. So overall, the frequency domain plots line up very well with the predicted values for the aliasing. Some small errors did occur, such as when some of them should be 0, they're actually 1. This is due to flaws and variations in the potentiometer, or perhaps small inconsistencies in my timing loop, or other similar causes. Going on to exercise 2, we will look at the square wave on the here. So you can see 10 Hertz, 30 Hertz, 50 Hertz frequencies present in the frequency domain plot. And then if we go to switch this to the triangle wave, you can see that the 10 and 30 Hertz and even the 50 Hertz frequencies are still present, but much less pronounced. So you can see that and that. And so in the square wave example, you can very clearly see the presence of a Fourier series to create the square wave, with the largest amplitude occurring at the natural frequency of 10 Hertz, and then all the odd integer multiples of 10 Hertz, so 30, 50, and 70 have important amplitudes. But in the triangle wave, the amplitudes of these integer multiples are much reduced.